friends, in this session we will be discussing about design of asynchronous sequential circuits. In this section, the various design steps of asynchronous sequential circuit through an example will be explained. The problem: a digital logic circuit is to be designed that has two inputs A and B and one output X. X goes high if at A is equal to 1 and B makes a transition from 1 to 0. X remains high as long as A is equal to 1 and B is equal to 0 are maintained. If any of A or B changes at this time, output X goes low. The timing diagram corresponding to this problem is shown in the figure here. If you will see, when A is high and B is going from 1 to 0, the output becomes high. The first step is to develop the state transition diagram. From the problem statement, we have to develop the state transition diagram using, say, Moore model. The state symbol and output at the state is shown together with a circle in this diagram. Let the initial state be considered as A when A B is equal to 0 0 with output 0. As long as AB remains 0 0, the circuit remains at A. Now, as soon as one of A or B changes, the circuit may immediately move to the different states. Here we are having the state transition diagram. Here we are having A, which is having the output 0. When A and B is 0 0, it will remain in this state. When any of A or B changes, it will either move to B state or to C state. Since A and B cannot change together, a constraint we have to adhere to this asynchronous design. At state A, if input AB is 0 1, the circuit goes to the B state having the output 0. If AB is 1 0, it goes to the C state and the state 1 1 is prohibited. Both B and C, they generate the output 0 as they have not yet fulfilled the condition stated in the problem for assertion of output. The circuit remains at B for AB is equal to 0 1. If AB changes to 1 1, then it will go to the state D. This arrow is wrongly directed. It should be directed in this way, and this arrow should be here with output X is equal to 0, and if AB becomes 0 0, it will go back to A. Similarly, the circuit stays at C if input stays at 1 0 but goes to D if AB changes to 1 1 and goes to A if AB becomes 0 0. Now at state D, input AB is equal to 1 1 and if B becomes 0, then condition for output X is equal to 1 is fulfilled and the next state E for AB is equal to 1 0 shows output as A1 here. The circuit remains at state E as long as AB is equal to 1, 0. It goes back to the state D if AB becomes 1, 1, because if B again goes to 0, output should be high. However, at E, if AB changes to 0, 0, the circuit goes to the initial state at A. As AB becomes 1, 0, falling 0, 0 will not assert the output. Permittive table. The next step is to form state table from state transition diagram. Often we can skip step 1 and directly go to permittive table from problem statement. Permittive table prepared from state transition diagram is shown here. Here, if the value of AB is 0, 0, it is at A, which is a stable state. If AB is 0, 1, it will go to B. If it is 1, 0, it will go to C and the output is 0. Similarly, B, if it is 0, 0, the state will be A. It is 0, 1, it will stay at state B, which is stable. At 1, 1, it will go to D, and for 1, 0, it is don't care, and the output is 0. Similarly, we are having the values of C, D and E for different values of 0, 0, 0, 1, 1, 1 and 1, 0 at AB. Now note that each row in this table has one don't care state. The don't care state in each row comes with asks for both the input variables to change to move from stable state, a condition not allowed in asynchronous sequential logic. Here it changes from 0, 0 to 1, 1. Here it is 0, 1 for B, and here it becomes 1, 0. Similarly, here both the inputs will change. That's why we are having the don't care condition. The don't care states have been given suffix like 1, 2, which is not necessary. However, this will help in the next step where we check state redundancy. In the table, if all the rows representing a state has only one stable state for all the possible input combinations, and it is termed as permittive table or permittive flow table or simply flow table. State reduction. It is always useful to check state redundancy before going for actual circuit design. Removing redundant states help in generating the circuit in a simpler way and with less hardware. The implication table has been used in this example to remove redundant state, if there is any. The implication table drawn from permittive table and state reduction is shown in the figure here. Now, to draw the implication table, as we have discussed earlier, we are having 5 variables here, A, B, C, D, E. We have to write down 4 here, B, C, D and E, and on the horizontal line we have to write the variable A, B, C and D. We do not require the cross section of AA, BB, CC, DD and EE. So we are choosing one less variable. Now we have to see the relation between A and B when they can be equal. Now first of all check the output. Since the output of A and B they are equal, so A and B can be equal if D is equal to don't care 1 and C becomes equal to don't care 2. Similarly, check for the relation between A and C. We see that the output is same, so they can be equal. Here they are equal if B is equal to don't care 3 and D is equal to don't care 1. Check for A and D, output is same. A is equal to don't care 4, D is equal to don't care 1, C is equal to E. A to E, since their outputs are different, so we cannot make any equivalence between these two. That's why here we have placed a cross. Now we have to go for B. B with C. If B is equal to don't care 3 and C is equal to don't care 2. B with D, if A is equal to don't care 4, E is equal to don't care 2. Similarly, between C and D, A is equal to don't care 4, B is equal to don't care 3, C is equal to E. C and E, no equivalence. Similarly, for D to E, no equivalence. Since E state cannot be equivalent with any of A, B, C and D, we put double cross right in the beginning for row E of the implication table. Now, since C cannot be equal to E, so this condition cannot be taken. This condition cannot be taken. So we are left with if D is equal to don't care 1, C is equal to don't care 2 and X is equal to and B is equal to don't care 3. This is how the new primitive table will look like. Here these two are equal, A and C are equal, so they can be removed and we are having this reduced table, and this is the state diagram for the reduced table. State assignment. This step in asynchronous sequential circuit design has to be done very carefully so that a valid state transition does not require two or more output variables to change simultaneously, which may lead to racing problem. In this problem, there are three states in the reduced state diagram which needs two variables to represent them. We cannot avoid any two variables changing together in one or more occasions for the reduced state transition diagram. We are having the variable ADE. A is represented by 0, 0, D is represented by 0, 1 and E is represented by 1, 0. Now, in this, there are two occasions when there are two variables which are changing. First, when going to from D to E, 0 is changed to 1 and 1 is changed to 0, and second when we are going from E to D. So we have to take care of this situation. A representation of 0, 0, 0, 1, 1, 1 requires two variables to change only once, where E changes to A, this one. The solution to this may be found if the unused fourth combination of two variable representation is used as a dummy state, say phi, between E and A. Let us represent the states in this problem by variable pq in the following way: A is equal to 0 0, D is 0 1, E is 1 1 and phi is 1 0. Note that phi is an unstable state, and before the input can change, it goes to the next stable state A. We represent state variable by P and Q, and the corresponding feedback variable are represented by small p and small q respectively. These are the reduced stable and reduced state transition diagram. And now with the introduction of phi, this becomes the modified state transition diagram. Now this is represented by A 0 0, D is represented by 0 1, E is represented by 1 1 and phi is represented by 1 0. The next step is to find out design equations and circuit diagram. We use Karnaugh map to get expression of state variable P and Q as a function of input A, B and the feedback variable P and Q. The equation derived from the K map are shown here. A is 0 0. Here again A is 0 0. These table we are taking from here, and the modified table is made from this state diagram. Now from this take the first values 0 0 0 0 0 here and solve the K map. We will get P is equal to Q B bar. Similarly, take the second values here 0 0 1 0 0 0 1 0, don't care 0 1 1, don't care 0 1 1 and solve this. We have Q is equal to Q A plus A B. Find out the value of x from PQ. It becomes x is equal to PQ. Make the circuit diagram from this one. These are the various design steps of the asynchronous sequential logic circuit. Now that we have seen all the steps in asynchronous sequential logic design, we are in a position to appreciate how complex the process is compared to synchronous sequential logic design. Thus, the latter is preferred if issues like speed, clock skew, etc. are not of critical importance. This discussion has the reference Digital Principles and Applications by Leach, Malvino and Saha, 7th edition, Tata McGraw-Hill, New Delhi, 2011. Thank you.